Hello everyone, and thanks for joining us. On behalf of the Environmental Finance Center Network, I'd like to welcome you to today's webinar, Water Loss Auditing, Navigating AWWA's Infrastructure Leakage Index. My name is Tess Clark. I work here at the Syracuse University Environmental Finance Center. And before we get started with our program, I'm going to quickly go over some logistics and just talk about our network and our Smart Management for Small Water Systems project. So for some logistics, during today's session, everyone will be kept on mute to ensure audio quality. If you have questions, just type it into the GoToWebinar question dialog box anytime throughout the session. We have online with us James Markham and Haley Hajic. Haley will be queuing up your questions and facilitating a Q&A at the end of the session, so feel free to send us those questions and we will get to them at the end. If you are having technological difficulties, feel free to also use that box and we will do our best to help you. We will be making today's slides available as well as a video recording on the EFCN website. You can reach that website at www.efcnetwork.org. Please allow 2 weeks for the processing and posting of these materials. Here's a map of our registrants today. We had, I believe, over 350, so welcome everybody. As a registered attendee, you can receive a certificate of attendance for participating in this webinar. This webinar has not been submitted to licensing agencies for pre-approval of continuing education credits, so you will need to check with your licensing agency directly if you're interested in receiving credit. You must attend the entire 60-minute session by logging into GoToWebinar with your unique registration link. Your certificate will be emailed to you within 30 days of the webinar date. All right, this session is one of several webinars conducted by the Environmental Finance Center Network for our Smart Management for Small Water Systems project. The EFCN provides training and technical assistance to small public utilities in all 50 states and 5 territories to help local systems achieve and maintain compliance with the Safe Drinking Water Act. And here you can take a look at our team. You can see we have networks in most US regions. And here are some of our areas of expertise. You can see that we work across asset management, rate setting, water loss control like we'll be discussing today, and many more. We also have a small systems blog. Our blog posts feature lessons learned from our trainings, descriptions of tools, and also small system success stories. And one last resource that I want to point out to you before we really get started is our funding sources map. This is a tool that can help you find the major sources of funding for drinking water infrastructure projects for your state or your territory. Here's how you would access those tables. On the EFCN homepage, go to the Resources tab and then click Funding Sources by State, like you can see on the slide. Then you should be able to see a map. That will take you to a map of the country, and if you click on the state that you're interested in, you will find a PDF table with the relevant sources of funding. The table looks like the image on the left of the slide, and for each program, it includes the name, a short description, and some contact information for a person that you can reach out to. Before I turn the presentation over to our experts for today, I'm going to quickly start off with some polls. Our first poll is, what kind of water or sewer utility do you operate? So just go ahead and tell us if you're a for-profit system, local government, a not-for-profit system, a different type of water utility, or not a water system. I'm just going to give you a couple more seconds to respond. And I'm going to close this poll in 3, 2, and 1. Okay. And here's the results. You can see that most people online today are local government or municipal or county systems. That's great. And we do have a fair showing of non-water systems today. Welcome. I think this will be valuable for everyone. All right, next. What size water or sewer utility do you operate? So just go ahead and tell us if you're a very small system. We want to know if you're serving 500 or fewer people, all the way through a larger system if you're serving 10,000 or more. It's valuable for us to see where everyone's coming from today. So I'm going to go ahead and give you just 3 more seconds to put in your response. 3, 2, and 1. And just to take a look at everyone's results, it looks like the majority of folks online are 23% large or very large systems. So thanks for coming. And on that note, I'd like to introduce James Markham. James is a research scientist at the University of New Mexico Southwest Environmental Finance Center. So welcome, James. James, are you with us?
I am with you. My screen should be up. Yeah, looks like we're good to go. So thanks everybody for coming to today's webinar. And based on some of the responses that you put in your registrations, I know that most of you are familiar with auditing, although many have not necessarily participated in a water audit and may not have a lot of knowledge about the sort of esoteric metrics that are buried within it. So I'm going to start with just a little bit of an overview of water auditing in general, and then move on to the metrics that we're going to be talking about in more detail today. So water auditing is based on the idea of a water balance. The idea being that some amount of water is going into your system, and that has to equal the water that comes out of your system. That's basic physics, conservation of mass. Water may appear to disappear, but it doesn't actually. And then what the water audit and the software that we use to do that audit with help us do is to essentially estimate or calculate the quantities that are going into the system and the quantities that are coming out of the system. And if we subtract the out from the in, that leaves us with a volume of real loss. This is, the water that's essentially leaking out of our pipes. This is a slight simplification, but this is basically how it works. And it's really important to recognize that the accuracy of a water audit really depends on the accuracy of the data that goes into it. As with any mathematical model, if you put garbage in, you get garbage out. And one of the quirks of the water audit software is that if you overestimate inputs, those overestimations show up in the audit as real loss. Similarly, if you underestimate inputs, they reduce the real loss number. Sometimes this is really obvious because you end up with a result with negative water loss, which is physically impossible. But it's important to recognize that this is sort of a top-down set of calculations that then needs to be verified with a bottom-up component analysis, which we'll talk about a little bit later on. It's important when you are looking at your data to realize, the water audit has summary data as input. So all of the water that you put into your system, all of the water that you sell to your customers, you really need to review your data and look at the data sources and how those summary numbers are calculated to make sure you know what's actually going into your water audit. As our old president, Ronnie Reagan, used to say when he was talking about nuclear disarmament, trust but verify. This is basically the way I treat summary data, and I think it's a very good idea. Trust the numbers that you're getting, but make sure you understand where they come from, particularly when you're doing estimated volumes for things that you don't have metered, and make sure you keep good records of how you came up with those values. The water audit software gives you several metrics. This is a screenshot of an actual audit. And the performance indicator tab thereon, and you'll see up at the top in the red, you've got a water audit data validity score out of 100. Each of the audit data points that goes into it has a data validity score that's based on policies, procedures, and practice, which sort of act as a proxy for rating how good that data point is. And then there's a weighted average that gives you for each of those, and that gives you this final score. And then you get a bunch of system attributes, apparent losses, which are your financial losses essentially, or things that are paper losses. They look like real losses, but they're not. Real losses, which is water that's leaking out of your system. This metric, unavoidable annual real loss, which we'll be talking about in great depth today. It costs some things, it gives you financial indicators, and it gives you these operational efficiency metrics, which depending on the size of your system, it may calculate some or most of these, but usually not all. So it'll give you real losses per service connection per day, or per length of main if you have a sort of less dense system. And then it gives you the current annual real loss, this calculated real loss lump sum number. And the final metric that it gives you, which is the focus of today's talk, is the Infrastructure Leakage Index, which is your current annual real losses divided by this unavoidable annual real losses. The idea sort of being that if your current losses equal your unavoidable annual real losses, you'll end up with a score of 1, which implies perfection, but as we'll see a little bit later, that's not actually typically the case. Some typical ranges, I'm sure some of you want to know this. As rules of thumb, when we're sort of evaluating the results of water audits, we expect losses per connection to be somewhere between 20 and 200 gallons per day, losses per mile of main somewhere between 400 and 4,000, and ILIs values to typically fall somewhere between 2 and 10, at least with systems that are starting out. And it's important to recognize when you're looking at these, there's an order of magnitude difference between some of these values, particularly with the real losses. So there's kind of a wide range of valid results. This particular audit has a very low ILI. This happens to be from a pretty tight system that has a very good asset management program in place. It's important when you're doing your water auditing to have a sense of reality about it. And for those of you who are online who are maybe new to water auditing or new to the water world in general, you are never going to have zero water loss. It's just not realistic. All systems leak to some extent, and it's really a question of keeping that leakage to an economically reasonable amount. If you do end up with a water audit that says you have zero leakage, there's a very good chance that your data is incorrect. But even that is a win because it lets you know that there are points in your data acquisition and collection and storage and analysis that need to be improved. One of the big things that comes out of the audit is this Karo, your current annual real loss. This is a lump sum value of what's leaking out of your system, essentially. It contains a component of technically unrecoverable losses, and I say that they're unrecoverable because through typical means of finding leaks, these are leaks that will not show up. This is, background loss that you can't hear using an acoustic mic, things like that. There is some amount of loss that you could recover, but it's not really economically efficient to do so. As with most things, there are laws of diminishing returns with regard to reducing water losses, and after a certain point, reducing the loss becomes more expensive than the value of the loss you're getting. And then there's obviously some economically recoverable amount of loss that you can attack. And the audit processes and the processes that you engage after doing an audit help you look at these. There's sort of 4 basic leakage control methods or categories that we use, active leakage control, and by this I mean, leak detection surveys, flow monitoring, things like that, night flow analysis. Obviously, optimizing your repair activities. If you can fix your leaks faster, you will lose less water. Pressure management is also a big one. There's a direct correlation between reduced pressure and reduced losses that we will also talk about a little bit in the future. And then system rehab and renewal. Obviously, not every system can replace all of its pipes, but that is also an option. The real question is, which of these tools do you use, and what is it that you're actually aiming for? And it really depends on the nature of your losses. One of the things that you really need to do is identify and define what your problem is before you start proposing solutions for them. What you're really looking for is an economic leakage level. There's a break point where the cost of reducing real losses exceeds the value of those recoveries. In other words, you don't want to spend 20 bucks to save 10 unless there's a good non-monetary reason to do so. And these are dynamics that vary from system to system. I like to look at water loss through sort of a triple bottom line of financial, social, and environmental costs. So the dynamics at play here in the Southwest, for example, where we have water scarcity, are going to be different than maybe up in the Northeast or the Northwest, where water is plentiful. That being said, at least two of these leakage control methods can pretty much be applied by just about anybody for, I think, very little cost. Optimizing your repair activities is something that you can look into, and pressure management as well. Not every system can reduce its pressure. Obviously, you have to be able to pump water up and over hills and into your tanks and meet your customers' needs. But there are a lot of systems that run at inordinately high pressures for no real reason that I can see. And in those cases, lowering pressure can actually have a net positive effect on your real losses. But as I said, it's really important to identify what your problem is before you start applying tools. There's no safe silver bullet. You need to have an ample toolbox of leakage tools and know when to use them and how to use them. As my dad used to say, when all you've got is a hammer, everything looks like nails. And as a perfect example of this, I know of a system here in New Mexico that had about a decade or so old PVC system, and based on some back of the envelope calculations and anecdotal evidence, thought that they had a leakage problem, and the one tool that they knew about was leak detection. So they spent $10,000 on a leak detection program that didn't really find any significant leaks. And then they didn't believe the results, and they did it again. That's an example of applying the wrong tool. Their real issue was meter calibration and their data inputs. So in general, water audits, help you identify what's going on in your system. They help you evaluate whether you have a non-revenue problem and whether that problem is due to real water loss, leakage from your system, or apparent loss, essentially water going to customers that you aren't getting paid for but should be, or, as is usually the case, a combination of the two. It provides us a bunch of metrics and gives us information about costing those. But one of the things that it doesn't really do is categorize those losses. It gives you a lump sum, and it's not going to tell you whether your losses are from breaks, background losses, or tank overflows. That requires further investigation, but the audit is step one. And I think the most important thing that doing a water audit does is that it gives you a great opportunity to build a team within your organization and review how you are running your business. And I really can't emphasize enough that water distribution, is a business, even though we don't often run them that way. So that's the end of my review. Let's look at the Infrastructure Leakage Index, which is a metric that a lot of systems tout. I've been to many conferences and heard systems talking about their water loss performance in terms of their ILI. Folks like to brag on it, but let's talk about what it really is. I want to start with a paraphrase of a quote from George Box, who's a British statistician, and that is that all models are wrong, but some models are useful. And I think, the idea here is that what we would like to have is a combination of perfect data, a perfect model, and get perfect results. What we actually have in reality, particularly in first-time audits or early in the stage of the audit process, is imperfect data and imperfect model, because there are estimations, there are assumptions made both in the water audit model itself and the metrics that go into it. And what we end up with is imperfect results. That being said, despite the fact that they might be imperfect, they are still very, very useful. But we have to have, add a caveat to that. They're useful for specific things, and we need to understand what goes into these metrics to sort of understand their validity. So Infrastructure Leakage Index, what is it? What is it for? It's touted as the best indicator for comparisons among systems, best applied after sufficient water audit data validity is achieved and all justifiable pressure management is complete. That's kind of a mouthful, but that definition alone should dispel some of the myths about it. It's not your audit grade, and it's not your performance grade. It's a comparison metric. To look at it in terms of an analogy, what you're seeing here is two trucks of vastly different scales. What kind of metric would I use to compare these two? With water systems, we have something similar. We've got, different pressures, different sizes, different materials. different layouts, different connection densities, and the idea was to try to develop something that would allow a comparison between systems with these different characteristics. And it's a way of sort of benchmarking performance, doing an apples to oranges comparison. So, quick review again, ILI, it's your current annual real loss over your unavoidable annual real loss. And I have a little bit of a problem with that name because it implies a level of certainty that I don't think is really there. But it comes out as a dimensionless number because the top one is gallons, the bottom is gallons. And it's calculated using some very basic parameters from utility. A lot of folks, when they're talking about this, sort of think of 1 as the magic number, that if you've got an ILI of 1 or close to 1, that you're perfect. An ILI of 1 is not typical. That being said, I've looked at several thousand water audits from around the country, and about 18% of those have ILIs that are actually below 1. Now, a large percentage of those are because of bad data, but some of them are actually legit, which sort of begs the question, if the value I'm calculating is unavoidable loss and my actual current loss is less than that, is that unavoidable annual real loss number accurate? And then we'll dig into that here in a second. Just for reference, a typical range of ILIs, somewhere around 1 to up around 8. These particular utilities are taken from the 2017 WADI data set. This is an AWWA initiative to collect validated water audit data over a number of years. And you can see we've kind of got a wide range here, and these systems are of wide-ranging sizes. So we've got this ratio, but to see whether it is actually applicable, we really kind of need to look under the hood a little bit and understand how these are calculated and where they come from, and some of the uncertainties that are involved with these numbers. So the Karo, the current annual real loss, that's a figure calculated by your audit based on the values that you give it, all of the inputs, all of the outputs, and then some assumptions about things like theft if you don't have your own records. It's really important to remember that small metering errors can lead to large margins of non-revenue water and show up as real loss or lack thereof. And sometimes it's a little hard to tell how far off you are. And it's important to also recognize that the Karo doesn't categorize your losses. We talked about this at the beginning. It gives you a lump sum. It doesn't tell you whether your problem is background leakage or tank overflows or a combination of the two. The trickier part is the unavoidable annual real loss calculation. One definition is that it's this theoretical reference value representing a technical low limit of leakage that could be achieved if all of today's best technology could be successfully applied. That's a definition in one of the tables in the M36 manual. There's another definition in there that talks about a system that's well managed and in good condition at an average pressure level. These are not exactly the same thing, and they leave some room for interpretation. I'm going to sort of paraphrase, combine the two, and just talk about it as a theoretical low limit of leakage. It's worth noting that the UARL formula and the ILI are based on an international study that was published in the late 90s. It used data from 24 systems from around the world. I think it was 20 different countries. It's been evaluated and reevaluated and fine-tuned a lot over the last 2 decades. These are performance indicators that are used extensively in Europe as primary performance indicators. A lot of the studies that have been done have actually expanded the size or the range of systems that the UARL is applicable to, generally applying it to smaller and smaller systems, which is where you end up with these systems that have better than average or better than 1 infrastructure leakage index numbers. And there's some speculation that that is a result of smaller systems being able to find and address leaks quicker. That being said, they're not without their detractors, and we'll get into some of the reasons for that as we go along. But the important thing to think about here is that it's a theoretical reference value. It doesn't refer to specific kinds of losses. It's based on tests in district metered areas in the UK in the 90s that have then been cross-checked with extensive testing in Australia, New Zealand, and Germany and Austria. But I don't know if it's as universally applicable as we would like to believe. It doesn't refer to specific kinds of losses, but oddly enough, it's based on specific kinds of losses. And it's an empirical formula. It's not like a formula that's derived from first principles, like starting with, force equals mass time acceleration and working our way up from that. It's based on a review of published data relating to break rates and flow times and flow rates, and there are a lot of assumptions built into it. So let's talk about some of the factors that we know actually impact real loss. In the real world, and if you go and look at the literature, there are articles about soil type affecting metallic pipe. That can affect your real losses. Materials can have an impact. The weather fluctuations in your system have an impact. There's studies that show that break rates in areas that have big temperature swings are higher than in areas that don't. How well your pipes were installed is going to impact your break rates and therefore your real losses. The average break frequency in your system, flow rates, time is a big factor. Time both for the discovery of leaks and repairs and the time to do the repairs, et cetera, et cetera, et cetera. Of necessity, the UARL and the ILI ignore most of these. If you tried to factor in everything that actually had an impact, you'd end up with an unwieldy formula that was not useful. So this is sort of a necessity, and what the originators did is they looked at things that had a big impact and verifiable and tried to narrow it down into something that was workable. And so it uses 4 variables from your system to calculate this value, which is a very small number. It looks at your length of mains, which includes your mains and your hydrant leads. It looks at the number of connections that you have, both active and inactive. It looks at the average length of your service line. This is assuming that your meters are not at the curb stop. If your meters are at the curb stop, this piece drops out. And then the biggest factor in the whole thing is average system pressure. And this is a place where I think, as a practical matter, there are problems with these calculations, because to calculate these values, you need to have an average system pressure for the year for your system. And I have seen a lot of systems that do not have a solid handle on this number. There's a lot of particularly smaller systems who don't have accurate pressure models. So the biggest factor in the formula often ends up being a little bit of an educated guess, which is why I think it's you have to be careful about reading too much into the values that come out of these metrics. There are some basic requirements for this formula to even be applicable to you, and the requirements are a little bit more complicated than this, but a good shorthand is 35 psi and at least 3,000 connections. What you actually need is the length of mains times 32 plus the number of connections to be more than 3,000, but I think this is a good enough shorthand. If you don't reach these thresholds, the water audit simply does not calculate these values for you. This is the formula. So 5.4 times the length of your mains plus 0.15 times the number of connections plus 0.75 times the lengths of your service lines. Add that all up, multiply it times the pressure times 365 days. That gives you a volume. The units are a bit weird, but it does work out to a volume. And so we know what the variables are. Those sort of make sense. Let's talk about the coefficients. And by that, I mean, the 5.4, the 1.15, the 7.5. What are these values based on? And more importantly, what are the assumptions that are going on here? Now, the values are based on research and public studies about mainline breaks, service line breaks, and background leakage. A lot of this work was done by Alan Lambert. I'll give you some information about him a little bit later, but he's kind of the godfather of water loss and has a really deep background in this and has done a lot of research. And what he and his collaborators did is they basically looked at all of this and came up with a matrix to evaluate background water loss. And it looks at the three main infrastructure components, so your pipelines, service connections, main to curb stop, and your service connections curb stop to meter. As I said before, if your meters are at the curb stop, this bottom line disappears. That's often the case here in the Southwest, but for example, up in the Northwest, the Northeast, where it gets really cold, meters are often in people's houses, so you have to consider that length of service line as well. And what they did is they came up with sort of ideal rates for background leakage, reported leaks and breaks. So this is, breaks that you find in sort of the ordinary course of business, or that your customers report to you that you go fix, and unreported leaks and breaks. And these are those leaks and breaks that you find through active looking, so doing leak detection, doing district metered surveys and things like that, night surveys. And so if you look at this in its component form, it looks a lot less simple. You've got these flow rates per mile, you've got durations for each of these components, and it's really difficult at its face for me at least, to say that this applies universally to everybody. If you sort of calculate these particular values out, and I want to note that these particular values happen to be at a reference point of 70 psi. As you raise and lower the pressure, the values change a little bit, but at 70 psi, what you're looking at here is approximately 75,000 gallons a year in background leakage on your mains, reported breaks of about 43,000 and unreported breaks of about 25. So what this sort of points out is the idea that, number one, your background leakage is probably going to be significantly higher than your reported leaks and unreported breaks, particularly when it comes to service connections, and even more so when you're responsible for the actual service line. And the first rate is a per mile per year. The bottom two are based on connections. So if you've got a very densely connected system, these service connection loss rates in the UARL calculation can kind of swamp the mains. So we've got an idea of what's going into this. Let's talk about some of the issues that people have with the UARL. Now, there's a little bit of a disclaimer here. What follows is based on a lot of published articles, our observations at the EFC, and some of my own research. I've been working on this for a couple of years now. I focus on break rate data, and so I've been digging into this for a while. A lot of folks look at the UARL and the ILI and think they are great metrics. There are a lot of folks that disagree. Me personally, I kind of take them with a grain of salt. My view is a little bit more in the middle. I think they are useful for rough system comparisons, but if and only if you've got solid data to begin with, and the underlying assumptions that are in that UARL calculations actually somewhat match the reality of the system that you're looking at. And I think that given the state of water auditing in the United States and data collection, and the fact that there is a lack of uniformity in that, I don't think we can say beyond a reasonable doubt that these are necessarily as valid across the board as many folks would like them to be. And I say beyond a reasonable doubt because in my earlier career I was an attorney, so I have a tendency to look at things in those terms. So specific issues, pressure, I think, is a bit of a problem or a bit of an oversimplification in the formula. We know that there is a relationship between leakage and pressure. At high pressure, a break leaks a lot. At low pressure, it leaks less. but it's not a linear relationship. There are a lot of studies that show that background leakage typically varies with pressure on a power rule, so it's not linear. What that means is that as pressure goes up, the leakage goes up as well. So you end up with this curve. Similarly, with leakage related to pipe bursts, that can vary with pressure increases and decreases to anywhere from the power of 0.5 to 1.5 or more. So that dotted line is kind of a linear representation. And how the power rule applies really depends on the kind of break. So fixed area leaks like ring cracks and corrosion holes tend to be on the lower end of the scale, around 0.5, which basically means if you're looking at that in a linear manner, you are underestimating at low pressure and overestimating your URL at high pressure. And things like splits and flexible pipe tend to be on the higher range of that power scale. Now, obviously, you're not likely to get just one kind of burst in your system, and it's unlikely that all of your bursts are going to follow any one of these particular curves. And I think a lot of the original data was done with metallic pipe, which tends to have, fixed area cracks. So what we ended up with is a little bit of a simplification. The URL formula treats pressure in a linear fashion. And so the result of this is that you can get overestimates at one end of the pressure scale and underestimates at the other. And as a result of that, a low ILI might actually be the result of an overestimation of your unavoidable background loss. So that's one issue. And I want to show you how pressure reduction can actually impact your ILI. You remember one of the first slides we talked about the idea that the ILI should be considered after pressure reduction, reasonable pressure reduction has occurred, and here's why. So let's take a hypothetical system with these characteristics. We've got 3,300 miles of pipe, 210,000 connections, and just for ease of calculation, we're going to say the meters are at the curb stop, and you've got an average PSI of 60. If I plug those numbers into our standard formula, I come up with a UARL, sort of an unavoidable annual real loss of 1,085 million gallons. Now, I'm going to take that value and calculate an ILI for this system. Let's assume that the actual real loss in this system is 22 million gallons. We throw our formula together and we come out with an ILI of 2.23. So sort of indicating that our current annual real losses are a little over 2 times what should be economically achievable. So let's assume that we decide we're going to try and reduce our real losses by 15%. And we're going to do that by reducing system pressure by 10 psi because we live in a flat system and 50 psi is good enough. We're going to try and improve our repair response time, and we're going to do some leak detection. And let's say we actually meet that goal. We have a 15% reduction in our real loss. So at the end of our year, we do our audit and we recalculate these metrics for ourselves. So our Karo is dropped by 15%. It's now 2059. But because we've reduced pressure, we have to recalculate the UARL. Trust me on the math here. That's 904 million gallons, which gives me a UARL of 2.28, which is actually higher than the one we started with. So if you are only focusing on the ILI as sort of the end-all be-all of your performance, despite the fact that you have had concrete positive reduction and large reduction in your actual real loss, this metric seems to indicate that your performance is worse. And that's an issue, particularly if you focus too much on it. Real losses through pressure management can increase your ILI or may end up with an ILI that's exactly the same that you started with despite these actual real volume reductions. And that's okay because the volume matters more. But a lot of folks like to sort of glom onto a single number as a representation, and unfortunately, in many cases, the ILI is that number that they glom onto as a representation of their system performance, and this demonstrates very clearly, I think, why that's not necessarily a good idea. Another issue with water auditing in general and the metrics in specific is this idea of data validity and confidence intervals. The metrics are presented as specific values. If you remember earlier on, we had our data grade value, validated data grade on the top, and then the metrics listed below, and most of those metrics went out to 2 decimal places, which sort of gives you an impression of accuracy. Now, obviously, that data grade up there is a sort of a proxy for how accurate your data is, but it's an imperfect proxy. And I have some other issues about how those are calculated, but that's for another webinar. And it's also important to notice that if you're in Texas, you actually use a different scale. They've got a 1 to 5 scale for each of their data points, not a 1 to 10 scale. They've simplified it a little bit. But the result of this is that you have metrics presented as specific values when in actuality they're more likely a range. But that sort of plus minus range is kind of hidden in the data validity grade. Those data grades are based on concrete things. It's an evaluation of your policies, procedure, and data collection for those inputs and outputs, but it's imperfect. And you can't really say, okay, well, I've got a data grade of 50, and that means my numbers are accurate within plus or minus 20%, whereas a data grade of 60 means I'm plus or minus 15%. That is a fact, but it's not really shown in the audit as it's currently presented. There is actually an Austrian water audit software that does present its metrics as part of a range, and I think that is arguably a better way to do it. But again, it's not part of our current version, but the current AWWA software is actually being updated. There's a new version 6 that's supposed to come out, I think, within the next year. So we'll see if maybe some of these changes kind of get incorporated into that. And on the subject of data validity, systems that are new to auditing have a tendency to overscore their data validity, which then sort of reinforces this sense of certitude about the results of the audit. The Water Research Foundation did a project where they assessed the adoption of the AWWA's methodology and then found that about 21% of the results, self-reported data included implausible results, but also that the average data grades of those audits with implausible results were actually higher than those with plausible results. There is a definite trend as systems go through the auditor process year after year that there's an initial dip in the data validity grade, and this isn't because their data gets worse. I think it's just because there's a recognition over time that the data you started with wasn't as good as you thought it was. So there's some uncertainty that's built into this process that is kind of I wouldn't say hidden, but only dealt with somewhat indirectly in the way that the validated way the data metrics are presented. In actuality, you can calculate system-specific UARLs, and there's some studies that show that a system-specific UARL is unlikely to differ by more than 15% from the standard formula, but also that if you had a system with no unreported bursts, that the UARL could overestimate by up to 20%. Those are some pretty big numbers, and when you combine that with the fact that the Karo is difficult to accurately calculate because there are of necessity some estimations that go into them. You have to correct for meter errors, things like that. You have to make some assumptions about the amount of theft that's going on in your system. At low ILIs, calculating your current annual real loss to better than plus or minus 20% can often be very difficult, even in a fully metered system. So when you think about what that means for the ILI calculation, you've got two numbers with an unknown amount of uncertainty that could be as high as 15%, and then you're dividing the two of them to come up with a third number, which is obviously going to be even more uncertain than the original. So the takeaway from this is, not that these are useless numbers, but that you should think of them, I think, as more of a range than a fixed figure. So, using our earlier example of 2.23, if just for arbitrary sake, we say that our range here is plus or minus 20%, and I'm not saying that this is the actual number that you should use, but if you looked at that, that means you could be somewhere between 1.8 and 2.7. Those look very different, and if you're a board member trying to evaluate your system's performance, I think it's important to realize that there is this range that you might be looking at. It's not a hard and fast specific number, and certainly probably not accurate to within 2 decimal points. Fundamentally, what I'm saying is if your data isn't good, the metrics aren't reliable. There's an issue related to break frequency here. There are a lot of assumptions built into the standard formula about break frequency, how fast you're discovering things and how fast you're repairing them. All of those may differ wildly from your actual situation on the ground. For the reported breaks component, it uses 0.2 breaks per mile per year. So does that line up with your system, or is yours maybe a lot lower, like 0.02 breaks per year? There's 2 recent studies from Utah State, which did surveys of utilities in the US and Canada, and what comes out of that is that, as I think we all expect, there are wildly different break rates for different types of pipe materials. And if you look at those studies, now granted this is all self-reported data, but if you look at those studies, the break rate that the UARL formula contemplates actually only lines up with cast iron pipe. Other materials that they look at, different plastics and things like that, actually have lower average break rates, and those are average break rates, not like the low levels. Those are national averages. PVC is around 0.02. That's an order of magnitude difference, and if your break rates and response times are significantly lower than what is being used to calculate the UARL, you are essentially overestimating what you could potentially actually do. Other things to think about is the fact that when it's doing this calculation, it assumes that 25% of service leaks are unreported and that 5% of main leaks are unreported. Does this line up with the situation on the ground? I'm not saying that this data is wrong. This is based on good, solid data. But it's from a while ago, and most of it is from Europe and places like Brazil and things like that. The flow rates have been verified in a lot of places, but I don't think they're necessarily as universally applicable as we think they are. And I'm just going to show you a quick example of the impact on the unavoidable annual real loss calculation that can result from just changing a single factor. And in this case, that factor is the break rate. So I know there's a lot of data on here, and I apologize for this slide, but this is based on a real system from the WADI data, 5,800 connections, 240 miles of main, and a really high pressure, actually, 95 PSI. And this system had a current annual real loss of 246. That should be in millions of gallons. So if you calculate the UARL using the standard break rate and leave everything else the same, you come up with unavoidable annual real loss of 74.71 million gallons and an ILI of 3.3. If you recalculate that with a custom break rate, and this is not a break rate that I made up, this is actually based on a weighted average break rate for a system that I'm working with that is based on the miles of different pipe materials that they have and the national average break rates for those pipes. So again, this is an average, this is not a low level, but if you just change that 0.2 to 0.74, you end up with a wildly different UARL. It's 10 million gallon difference, and you end up with an ILI of 4. 18% difference by changing one factor. And I would like to note that Albuquerque's break rate is a lot lower actually than the value that I'm showing there. The point I'm making here is that if the underlying assumptions that go into that standard formula are inappropriate, then using the standard formula might also be inappropriate. The neat thing is that Alan Lambert actually has a spreadsheet that you can use to develop a system-specific UARL using assumptions that are specific to your system, so your break rates and response times and things like that, if you have that data. Mr. Lambert's website is here, leaksuite.com. Yes, there are 2 S's there. It is a really interesting website. If you like to geek out on this stuff, it's a good place to go. There are a lot of published papers. He's been working on this stuff for more than 2 decades. There's a lot of information about these metrics and what they mean and how they've been applied in different places. Available on his website. The spreadsheet isn't available for download there, but if you contact him, he will send it to you. That's how I got a hold of it. I just asked him for it. So that's a lot of information here. I'm going to give you a quick take, or my quick take on what this all means. And, you know, again, based on my observations, my research, and other papers that are out there. Number one, you know, the ILI is not shorthand for your audit grade. You know, if you want to use it as a bragging number, that's fine, but recognize that it's probably not as accurate as you think it is, and that's particularly true if your data isn't rock solid. It's not how you track real loss, and you certainly should not look at that metric in a vacuum. It's one of several performance indicators. They should be reviewed together in context. It's good for basic benchmarking, you know, comparing different systems with different characteristics, assuming the underlying assumptions are valid and your data is good. And I'm talking about the standard formula here. I think it's got limited value to a utility that's just starting the auditing process. It's really a reality check. You know, if you get a really low or really high ILI and you're, you know, not seeing tons of leakage, or, you know, you've got a really leaky system and you've got a really low ILI, that's kind of an indicator that there is something wrong with your data. But, you know, don't get a number and start patting yourself on the back and dig a little bit deeper. You know, work on your data. And I think it's important to note that the first couple audits often aren't very good. You know, data validity is not very good, and the results aren't that great. And usually that's because your data collection and storage and analysis processes aren't that good. They get better over time. This next bit is potentially a little bit controversial, but I don't think the standard formula is accurate enough to legislate on in the United States. So far, nobody's actually done this. You know, there's, I believe, 6 states that require water auditing. California has mandated third-party water audit validation, and I believe Tennessee has mandated minimum data validity scores, but I don't think it would be a good idea to mandate ILI requirements as a part of developing a water loss control program in states, particularly sort of given the fuzziness of the standard formula and the fact that the economic situation of every utility is different. And this is all about, you know, reaching an economically sustainable level of loss that works for your system with your current situation. You know, another fact to point out is that because of those size requirements, the ILI probably doesn't even apply to about 75% of the utilities out there because either the pressure is too low or they don't have enough connections. You know, I really think we need to study further and evaluate whether the components and the assumptions in that formula are appropriate across the board before anybody tries to make anything mandatory. I think we're probably going to see that there are regional differences that might want to be able to be taken into account. But I also think that this is a good place for the adoption of you know, GIS and asset management principles. I think those things are going to really pay off. When these formulas were originally developed, I don't think we had the data collection and analysis tools that are as robust as the ones that we have now. You know, a slightly less accurate but usable formula was acceptable. But I think, you know, with the sort of wider acceptance and use of GIS and asset management principles, I think we're going to get much better data, and we'll be able to dial in, specific material break rates and do, weighted averages, and much more easily calculate system-specific UARLs that will be more useful to individual water systems as they develop their water loss control programs. It's not useful for process benchmarking or developing specific loss control strategies. It's just kind of a benchmark. And seriously, do not use it for process benchmarking. I showed you an example before of how if you do that early on, you can end up with some very weird results. Look at them, evaluate them, but take them with a grain of salt, and really dig deeper. Do the component analysis. There's a link here to a component analysis tool from the Water Research Foundation that will help you figure out, what buckets your real losses actually fall into. Collect break data, calibrate your meters, improve your processes. All of these will have positive impacts on both your data that you're using to calculate these audits, and also, I think your water loss control programs, because if you capture this information, you'll be able to do a better job of seeing how you're doing. And quite frankly, even if you're one of those small systems that the ILI doesn't apply to, you should still be doing this, because there are real loss metrics that you can really look at, and I think they are far more important. What is your real loss from year to year? Your water production year over year. Can you track a reduction in breaks? Is your repair and response time improving? Hours spent on repairs, things like that. There's a lot of different metrics that you can use, and I think focusing on the actual real loss numbers and your data, and maybe at least initially not paying quite so much attention to the ILI would benefit all of us. So with that, I'm going to turn it back over. We've got a quick couple of polls, and then we'll open the floor for questions. And I know we're running a little short on time here, but I'm happy to stay on after to answer any questions that we can, and any questions that came in that we did not get to, we'll answer in a follow-up by email that will go out in a couple of weeks.
Awesome. So we just have some quick housekeeping to do. So the first thing I'd like to ask you is if you would like to subscribe to our EFCN blog. This is just a way for us to communicate with you. If we have any good insight on these tools, we'll share that. And it's just a great resource for small systems and large systems too. So I'm going to go ahead and close this one. And the next thing that I'd like to ask you, a really core component of our small systems project is technical assistance. So if you know that you need some help with your water loss auditing or just getting started, that's something that we can set you up with an expert to work on. So if you wanted to go ahead and respond yes here, if you are interested in technical assistance, I can send you a survey to check your eligibility, and then we can directly match you with an expert. Great, so I'm going to go ahead and close this in just 2 seconds. 2 and 1. And lastly, you should all have received in the chat box a link to an evaluation. That's something that'll help us be able to monitor this program, know if we're doing a good job, so feel free to take that as well. On that note, James is going to be taking questions, and Haley Hajek is going to be helping facilitate. So James and Haley, take it away. We've got about 3 minutes, maybe a little bit more, and you guys can always go over.
Okay, great. Thanks, Tess. So James, our first question here says, we struggle with bad registers and believe this impacts both our revenue and water loss. Can you speak more to this?
I assume by that they mean that their metering is a problem. And yeah, I mean, metering is often the low-hanging fruit in the water audit world. Bad metering often leads to high levels of apparent loss, so those accounting losses. I have a system that we worked with down in southern New Mexico where not only was there metering issues, but about 4% of their meters weren't actually even in their billing system. So that's instant revenue once we identified them that they could look to. I think without accurate metering, it is difficult to come up with accurate numbers, but not impossible. Meter calibration isn't the most expensive thing in the world, and if you're looking particularly at your customer meters, maybe not from a revenue sense, but from a data accuracy sense, you can always pull a number of meters and do tests on them. And see, if you can determine an average value that you are over-registering or under-registering. And there is a place in the water audit for those kind of corrections. There's an AWWA manual that talks about how to do that, how to pull a statistically valid number. And that can be done as simply as when I was in American Samoa, they were doing this. The utility pulled a bunch of representative meters of the different types and ages that they had, and they built a rig on the outside of their building where they had, at the very beginning, a meter that they knew was accurate, and then they placed all the other meters after it, and they ran water through it over time and did a comparison and tracked the various meter inaccuracies that way, and then applied that information back into their audit to come up with that correction. So there are some relatively inexpensive ways that you can do this, but yeah, if you want to have good audit results, you really do need to have accurate registration and metering. And if I didn't answer your question fully there, pop in another one and I'll try to answer it in the follow-up in the email.
Okay, and then this question really dovetails off of what you were just talking about, but we have a registrant that they do not have meters, and they're wondering if there's a way to use this program without exact usage numbers, or as you were speaking to before, it's really not accurate enough to use.
You can do estimations. There are values available for the average number of people per household in your area. You can get that from census data. If you're a very small system, you could actually go around and figure this out specifically. But there are average usage values, per capita, gallons per capita rates in different cities that are published, or different areas. They are typically lower in rural areas than they are in city areas, so you have to keep that into account. But you do have to recognize that it's always going to be an estimate, and that's also one of those situations where if you're doing a lot of estimating, you really have to look at the metrics with a grain of salt. That being said, if you focus on your inputs, if your input is metered, I think one way that you can sort of get an approximation is, do those calculations that I was just talking about, per capita usage and average number of people per household. But if you've got good numbers on your input, and you are collecting break data, so every time a pipe breaks, note when it broke, when it stopped, figure out what the pressure is on that pipe, estimate what your flow rate was during the period that you lost water. When you're doing flushing, do the same thing, do time studies, and track the things that you can. It's not going to be perfect, but it'll be better than a guess. Obviously, meters on everything is ideal, but as I pointed out earlier, even in fully metered systems, it is often difficult to get an absolutely perfect number, because basically there is no meter that registers perfectly at all flows. So there's always a level of uncertainty here. I think the important thing is that you start collecting the data and you start doing the audit, because even if you're doing estimates, as long as you're making good faith estimates and they're reasonable, your results are useful. It's one of those situations where you have an imperfect model and imperfect data, but you do get useful results.
Great. So changing gears a little bit, How do you recommend coming up with average system pressure?
That is really difficult. To do it accurately, I think you need a computer model. If you're a small system, you can use fire hydrant pressure. There is actually, I think there is, that's a deeper discussion, and it's kind of system specific. And you're welcome to contact us afterwards, and we can help you with this. But there are some guidelines in the AWWA M36 manual that give you an idea of how to do this on paper, where you sort of take elevation and pipe pressure and pipe size and things like that into account. If you're doing auditing, I seriously recommend that you buy the M36 manual. I think it's about $100. It's available through AWWA. It's kind of the Bible when it comes to this stuff, and will answer a lot of these questions in much greater detail than I can for you right now. And actually, come to think of it, check with your fire department, because there's a very good chance that they have done pressure tests on the fire hydrants in your system, and that is a really good starting place to sort of begin to do the calculation. But grab the M36 manual, the information is in there.
Great, and let's just do one more question. This question was asked early on, and you actually did answer it later in the webinar, but I think it's worth repeating. What is the current version of the AWWA Water Audit Software? I know you mentioned one is coming out soon.
Yeah, so the current version is version 5. It's available on the website for free. It's one of the few things that you can actually get for free on the website. You do have to give them your name and email address because we're trying to keep track of how many people are downloading it and using it, but it is free. We can send out a link to that software in the follow-up email where we give you written answers to all of these questions. But if you basically search, free water audit software, AWWA, in Google, it'll get you to the right place.
Great. Okay, well, again, we will provide answers for those questions that we weren't able to ask, but Tess, I think we're good to go.
Awesome. Thanks, everyone, for coming. We're going to go ahead and close this down. So thank you, and feel free to get in touch with any of the panelists or with me. You can contact us at smallsystems@syr.edu. Thanks.
Thank you very much.